Bachelor's of Engineering degree in Electrical and Electronics Engineering from Bangalore University in 1989. After that, ABB Limited Bangalore as an engineer and lead various projects based on control and relay panels. She has done an MSc in Power System from IAC and an MS in Software System from BITS Pilani. She did a post-graduation in Management for Executive from University of California, Los Angeles. Her area of expertise is power system protection and also in hybrid industries, which focuses on automation of wide range of different businesses. She has met. Now, on behalf of Power and Energy Group NIT Calicut, I may request Ms. Padmasri ma'am to carry over the session. Over to you, ma'am.
Over to you, ma'am. Welcome, ma'am.
Yeah, thank you. You should allow me to share, I think.
Yes, ma'am.
Yeah.
You can share now.
Yeah. Just give me a minute. Are you able to see my screen? Hello?
Yes, ma'am. Yes, ma'am.
Yeah.
Oh.
Okay. Okay, thanks a lot, Mr. Deepak, because I think we have been interacting for quite some time now for the last 2 months. And thank you for giving me this opportunity. Good afternoon, one and all. It's very encouraging to be virtually addressing an enthusiastic engineering community. Perhaps, as you all know, the topic of discussion will be AI/ML in power system or artificial intelligence in power system operations and control. Perhaps before we directly jump to the technology called AI or AI/ML, let us get acquainted with the buzzword. Everywhere we hear this word digitalization. Let us try to understand what this digitalization is. In simple words, digitalization is the process of converting data into value using digital technologies that are known, that are available. Perhaps now, so because you are using these words digitalizations everywhere, whether it is in the power system context, whether it is in the industry, manufacturing industry context, or it's in the financial context, social media context, everywhere we are talking about digitalization. So it is just a buzzword, but it's a simple explanation wherein we convert data to value using the digital technologies. So now let us start to look at the evolution of these technologies in the past 6 to 7 decades. We call it the technology S-curve. Why S-curve? S-curve because when a technology is just creeping in, only the early adopters are looking at it. So you will have a lower growth rate of the technology, and then there is a steep rise in its adoption, and then it stabilizes or goes down depending on the status of the replacing or the alternate technologies. So now let us focus on the coming decade, that is 2020 to 2030. Let us look at the kind of technologies that are there and the combinatorial effect of this technology. The cloud and mobile computing, big data analytics and visualization, IoT and smart machines, and smart everything. Because today we are talking about smart wallet, smart pen, smart laptop, smart mobile, smart everything. It has become smart everything. So now when you are looking at it, as shown in the and we are also seeing that, as shown in the graph, you are also seeing that artificial intelligence and quantum computing are not very far away from each other. Very far away from the impact that it is going to cause for the environment in general. The other thing is that, as you see in the graph, the combinatorial effect of all these technologies is unprecedentedly seismic. Probably the single most dramatic cataclysm, be it the manufacturing world or the power systems world. and perhaps it is also overhauling practically every conviction which we have had so far, be it control, monitoring, resource allocation, loss management, workforce involvement, asset handling, customer relationship, or environmental management. So in any aspect, you see these combinatorial effect of this technology so prevalent that even if you think about how you order on Amazon, how your orders are going through in different places, and how it tells you what you have to order next time, or who are the other people who have looked into it, and which are the other items, people who bought this item, what all they have bought, things like that. When they have to come and give you this kind of information, all these technologies are very prevalent in getting this kind of an information. Now let us look at power system sphere. The power system sphere is also undergoing a profound, even a dramatic change. Its drivers are many. Among them is the pervasiveness of the connected technology, because we are using communication, we are talking about Internet of Things, we are talking about software platforms, software as a service, cloud platforms, etc., and the data optimization, hyper personalization, and as a service business models. All these are really pushing us even in the power system field, and we are just at the beginning of this change. Critical to this success in this new digital industrial world will be the deployment of the right technology, preparation of the digital workforce, intelligent orchestration of both, embedding of the enterprises in the right ecosystem of business partners. So we are at the tipping point of this change. There is simply no better time to get grips with it. So we are looking at this kind of a background of technology when we are talking about how artificial intelligence has proliferated into power system also. Then we are looking at the ecosystem. What is it that we are calling as the ecosystem? Now, when you look at the increased capabilities, technology has moved, as we saw it, at an exponential rate. Computing power has increased. Data storage capabilities have increased. I'm sure you will all very well understand that if you looked at if any of you had some floppy drive or floppy disk or something like that, they were not more than few KBs of storage capacity which those floppy drives had. So today we are talking about terabytes and gigabytes, etc. The communication speed, we are now talking about 5G, virtualization of the data presentation. All these are the increased capabilities which we are getting. And then when you are looking at the usage of the sensors, increased visibility, we are using sensors everywhere. We are able to collect the data from all levels, from the process level to the plant level to the enterprise level. We are able to propagate this data there. There is a growing trend also to put sensors even in distribution networks. IEDs for protection behave like sensors. They have proliferated all the network. There is now perhaps a very less distinction between the transmission and distribution system. They can be viewed as a single entity because IEDs have proliferated everywhere. This enables automation and in the future autonomous operations as well. And increased availability of data, as we talked about IEDs. IEDs can be viewed as data producing elements which multiply as protective relays, load tap changers, voltage regulators, etc. Generally, the IEDs are capable of giving two kinds of data. One is the operational data, which is routed in real time to control centers for monitoring and control purposes. And the second one is the non-operational data, which is routed, stored, processed, and analyzed and accessible on demand to operation personnel and enterprise level to allow significant insights and value creation. So this is our ecosystem. So now where we are in a digitization world. We have the technology, we have an ecosystem which supports us. So what is it that we are finally looking at in the context of power systems? there is no way you can talk about artificial intelligence or machine learning without talking about data. That is the big data today, which we are talking about. We talked about IEDs giving out so much of data. So with the advancement in sensor technologies, and there are abundant data points now more than ever. So this amount of data is usually referred to as the big data. Logically, it is derived out of data. Includes this becomes the backbone of the AI technology. So we need to talk about a little bit on the big data, the source of data in the power systems, before we actually talk about the artificial intelligence itself. Now, when we're looking at it like that, if you take the case of big data, this involves more than just size of the data. We are not just talking about big data because the volume of data is very high. It is not just the size. It extends into the complexity, and it is also extending into the speed at which is collected. So that comes with so much more complexities, because if it is collected at that great a speed, you need a storage space, you need an analytics model which is also fast enough to derive insights from the data. So because basically what is data used for? The data itself has to be converted to value, as we talked about digitalization. When it has to be converted into value, first we have to derive insights from this data. So so from that perspective, if you look at it, big data has a lot of definitions and many self-referencing definitions, but logically it is coming from data. While data are generally any sensed output, big data involves data that are too big, as I mentioned, complex, and overwhelming to be analyzed by traditional methods. The pattern recognition, if you look at the data, it is not like looking at some current value and saying that, okay, this is already slightly above the 80% current value that we are seeing. This is not the kind of analysis that you can do with the amount of data that is coming in. So there is no traditional method to traditional methods will become extremely exorbitant to work with when we are really we will be overwhelmed if you are using traditional methods to analyze this kind of data. There are about 42 attributes which could be talked about in big data. That's indicated in a particular in some book where we talk about Industry X.0. But basically there are some 3 V's which really are the highest looked into attributes, and 3 V's with addition of 2 more V's. The 3 V's that we are talking about are the volume, variety, and velocity. And in this, velocity is very critical, because traditional methods could have still been applied if we were capable of allowing that kind of a time, meaning you collect it, and if you had enough time, we could still handle it. But the time is also a prime consideration. Now we have 2 more, that is the value and the veracity. When we are talking about value and veracity, it is when you are talking about value, it is identifying patterns, correlated data, and forecast measurements, and some kind of prediction which you can get from the data. Then veracity, when you're talking about we are really talking about security, data trustworthiness, meaning how much of this data is good enough to be used, how much of this is good data which we can use for further analysis. So that veracity is also very important. So there are 5 attributes of this big data which really are absolutely required. And now if you have to do this analysis of this big data, then comes the variety of machine learning methods which are used. Now in all these things in the context of power systems, if you have to look at, how do we really look at the future power systems? Why do we feel that the power systems are in that big data mode? because there is slowly we are already moving in the recent times. Also, there is a lot of proliferation of renewable energy, distributed energy, distributed energy sources all across distribution. And then we also have at a transmission level, we have solar farms and wind farms, which are renewable energy sources. So all these things have proliferated to a great extent into our grid. So when we are looking at this kind of a proliferation, there is a lot of decentralization also which is coming into picture. There is an expanded communication capability and monitoring abilities, and as mentioned, there are wider variety of sources. So all of these expanding smart grid, increasing penetration of Internet of Things, which means that you have a lot more data, expanding renewable resources, and microgrid considerations. All these things are at a high speed. So when we are looking at it at this level, so we are talking already about big data being available. So future power systems, you have no way of escaping the requirement of, meaning the availability of so much of data and the need to do the analytics on this data. So expanding penetration of smart grid is not just only expected for a future, it is already underway, as we all know. But along with the smart grid comes a multitude of logged customer data, power grid data, which can be analyzed to find power theft, improve the operating conditions of the grid at large. An IoT-enabled power grid allows the monitoring of the critical infrastructure, handling the big data and security problems. Increasing the decentralization through microgrids and nanogrids is perhaps not very far away. So all these things are the situation with the present or modern power systems, modern and future power systems. So now when we look at the situation, so now in the context of power systems also, we have n number of situations wherein the data we are able to collect and store large amount of data because of the changes that are happening in the power grid itself. What happens in this modernization of the grid? And why do we really do this modernization? Of course, when we were achieving the objective of grid modernization, there is a remarkable increase. Of the data available. Data for analyzing the power market, data from time synchronized phasors, also known as phasor measurement units, PMUs, which you would have heard, for state estimation, IEDs, SCADA systems, etc. This mainly, you would need to extract the insights mainly to enhance the power quality for the consumers, optimize the power system operations, meaning the cost of running the power system should be optimum. So we should be able to do it economically. The availability and the reliability of the power system should be good. The quality of the power should be good. So this is the requirement. So what happens during these times? Data, see, where there is so much of new data which is rich in information and which may provide insights, stimulate the research opportunities for the power system enhancement. For example, let us take the data from the PMUs. When we take the data from the PMUs, there is an optimal application of time synchronized phasor data, which leads to the development of wide area measurement systems. So VAMS is a powerful approach to identify inter-area oscillations in a large grid. So if you have to utilize the data from the PMU, you could easily utilize it, and you can look at it from a perspective of creating a stable grid, because you can identify inter-area oscillations in a large grid. PMU-based wide area measurements are also being used to provide remote feedback signals and improve the damping of the inter-area oscillations through specifically designed damping controllers. So, and you could have coordinated damping controllers, and these PMU measurements also indicate to you the fault tolerance limits also of the system. So from all this information, you really can attain the stability of the system. So these are all some of the use cases which have been there, and we have been solving these problems in isolation to certain requirements. But now with the availability of big data and the way you can attack the big data using machine learning, techniques or machine learning algorithms, gives us so many wide opportunities to make the power grid stable. A few other examples are also there. Risks in the electricity market. We don't have that kind of a market in India, but there is a lot of markets which have hourly price or of the spot markets, customer loads, renewable energy production. Even in India, you are already having the power purchase agreements with individual solar people who have homes with individual solar generation. There are power purchase agreements with them as well. But what we are talking about is a more deregulated market wherein hourly price of the electricity or the power keeps changing. We also can make an fairly accurate forecast of the load, energy production, and market prices, making activities of a generation company or an electric utility for producing energy. So and the electricity, we know, is a special commodity which is not easily storable. All the generated electricity must be consumed. In that instant, it was produced. So therefore, the producers and the consumers need accurate price forecast and establish the best strategies for their own benefits. So you have these kinds of examples wherein you really can use these are some of the use cases which we are talking about, where we directly can use the machine learning and artificial intelligence capabilities. So now we talked about so much of data. So now we also have to look at what are the data sources available due to this modernization. We have the IEDs, which are an important real-time data source. We can capture the user profile history, the PMU measurements, distributed energy resources, and these IEDs are also connected to, for protection of capacitor banks, etc. And they are connected to the sensors, actuators, breakers. So you get information from all the data sources that are available. So when the power system, which is behaving dynamically, you are able to get a real-time data. So you could do a lot of things if you had a capability to analyze this data in a faster and an efficient way. And there is also some other requirements to getting these things, meaning we are talking about the grid interconnection with Internet of Things. This is integration of ICT, that is the information and communication technology. This becomes a requirement. It has to be integrated. The communication network should be intelligent, integrated with high performance, highly reliable, robust, and flexible. It should also be responsible for data. Because it will be responsible for data collection, routing, monitoring, and management of all the active devices in the network. Hence, you need a robust communication infrastructure. Given this, when you are applying this IoT in a power system environment, we are already moving into a cyber physical system. That is, you have a lot of these physical systems which you see on the left-hand side of the figure, and then you are already collecting. All these are converted into data, and then they are going into the cyber world. And now so it's a complete because of the ICT. You are having a very comprehensive cyber physical system. So it is the integration of the IoT and the big data technology. So now when you talk about this, there are certain other requirements because of this, like latency, which is the network delay or the expression of how long it takes for the packets of data to travel, bandwidth, then interoperability and flexibility, because all of the data comes in some format, formats, protocols, etc. the data throughput, the rate at which the data transfer takes place. And then above all, because we are working in a cyber world, we are talking about cyber security. So we need to have cyber secure standards to be protocol standards which have a cyber security, what do you call, the cyber security features should be embedded in these standards. There should be privacy requirements. These are some critical issues which need to be already addressed. So this is what is the requirement that happens in a power system also, if we are really looking at usage of artificial intelligence in the control and monitoring. Okay, now we really come to the crux of the issue which we are talking about. We have said so much about big data, its source, requirements on communication networks. Also, we indicated that we must derive insights out of this data. We've also mentioned we will not be able to use traditional methods because of the vastness. Now we have to really look at the mechanism we use to convert the data to insights. So this is where machine learning is coming into. And here, here we use the support of machine learning, as I mentioned. There are a variety of machine learning methods which are generally employed. Machine learning is again a broadly used term which can be synonymous with pattern recognition, statistics, and data mining. Also, there are a variety of new methods which have recently emerged, like a large-scale neural network, which is also known as deep learning, which are capable to analyze and exploit the bigness of the big data. These methods have achieved significant advancements in image recognition, and we are also trying to use these kinds of technologies in power system big data analysis. Okay, so we also simultaneously hear about AI. Now we told so many things about machine learning, but we also hear something about AI, and we sometimes use them interchangeably. Invariably today, for safety, it is always AI/ML which is used. AI/ML is what is being used. So these are some things which are interchangeably used, and many times we are not very clear whether, if we are coming from our regular academic view, and we being electrical engineers, when we are looking at it, sometimes we are not very sure what is it that this is referring to. See, artificial intelligence perhaps is like the mathematics, or is like a science, mathematics or biology or physics or whatever you call it. But then machine learning is a subset of it, which means to say that AI is a general field that encompasses machine learning, but it also includes many more approaches that may not involve learning. So artificial intelligence is a superset, machine learning is a subset. And in the machine learning, if you're looking at it, artificial intelligence, if you're looking at it like science or mathematics, it studies the way to build intelligent programs and machines that can creatively solve the problems, which have been considered as a human prerogative till now. This was always a human prerogative, and now we are making the machine think and do it for us. So basically, one of the key features of this would be the ability to learn. A family of machine learning models is responsible for this ability. Their essence is simple. Unlike classic algorithm, where there is a clear set of instructions that convert incoming data into a result, the machine learning bases itself on examples of data that is available, the corresponding results that they are yielding, and then they derive a pattern in the data and the result, and they produce an algorithm that turns arbitrary data into desired results. So it is learning. Basically, it is looking at the data, looking at the result, and then creating a pattern. And then it is basically turning any arbitrary data at a later stage. So certainly this model requires a training time. So after the training is done, if you are having enough data for training it, then the model is capable of producing the desired result for an arbitrary set of data, or the test data, which we call. As we said, machine learning is a subset of the artificial intelligence that provides systems the ability to automatically learn and improve from experience without being explicitly programmed. You don't program it with the physics or the mathematical model. You don't program it with the physics-based models or the mathematical models. Instead, it is more trying to, you create an environment wherein it is trying to learn by itself. Just a minute. So in ML, there are different programs, different algorithms, for example, neural network that help solve problems. Now, if you're looking at deep learning or deep neural learning, it is again a subset of machine learning. And you would be having a neural networks to analyze different factors with a structure that is similar to the human neural system. So each node is assigned some activities, and then finally there is a layer. From that layer you have many hidden layers. From the input layer you move to the output layer, depending on how many, depending on the complexity of the data and the problems, you might have a number of hidden layers in between. Largely, ML can be classified into three main categories. One is supervised learning, where we are talking about system is trained based on some data examples, previously known results for each example. There are two popular tasks for the machine learning, the regression and the classification task. In a supervised learning, it's like a decision tree, meaning if this is the data, so this should be what you should identify it as, or this should be what you have to classify it as. And artificial neural networks are also examples of supervised learning. Support vector machines are also examples of supervised learning. Now, when you're looking at unsupervised learning, here what happens is there's a lot of data available, but you are segregating this data into two parts. One is the training data, and you still don't know the results. They are only looking at the data and the patterns in the data, the relationships in the internal relationships in the data, and based on that a model is created. And for, examples of this is k-means clustering, a priori algorithm, etc. These are the types of unsupervised learning. Then you have the third type of learning called the reinforcement learning. Here there is a reward punishment kind of an situation, wherein there are three stakeholders in the whole thing. One is the agent, two stakeholders from a perspective of stakeholders. There is an agent, there is the environment, and there is the state of the agent, and there is an action that you need to perform to change the state. And if the state is a desirable state, you will be rewarded, the program will be rewarded. Otherwise it will be it will have a negative reward. So from that you there are correct, so you decide based on the reward, the program is going to decide whether it's a correct action or a wrong action. So the reward identifies whether it's a correct action or a wrong action. So this, based on this, as a result, the system learns to develop an algorithm in which it receives the highest reward and the lowest penalty. So that will be the target for the agent. So for example, Q learning. Q learning is one method of reinforcement learning. And you have the life cycle model. Is most of the whenever you are creating a ML model, machine learning model, it has to follow this life cycle. One is you're having the objectives and the value levers, where you're defining objectives, risks, criteria for success, and also certain constraints. Then the data acquisition is there, where the data sources like PLCs, SCADAs, data storage systems, etc. And the data can be structured or unstructured. Then you have the model building and deployment. You validate the hypothesis to define the modeling objective. define the target, key input variables, dimensionality reduction, because you're having n number of data, meaning you're having a huge amount of data. So you would find a way to reduce the dimension of this data and build and deploy the model for prediction or diagnostic. Then model interpretation. The model interpretation is basically you communicate the insights and visualize the result. Then model sustenance, model monitoring, because the model has to be retuned always. The data can be something which the model has never encountered. So a retuning of the performance has to be done. The model has to be retuned and the performance control has to be planned. So from that perspective, this will be the life cycle of the machine learning model. Sorry. Yeah, now let us look at which are those kinds of use cases where there's actually whatever I am indicating here in this talk, there are a lot of literature already kind of available. There's a number of papers in the last 4-5 years. There are a number of papers which are based on machine learning. So there are a number of these use cases of power system operations which have been discussed in those literatures. See, the basic goal for us always in power system is to give quality electricity power in a most economical way, maintaining the power system stability and reliability. This will not change. So given this objective, there are many use cases. Perhaps some of the use cases are like this power quality disturbance. So when we're talking about power quality disturbance, it is increased use of energy, renewable energy, liberalized energy markets, and most importantly, the integration of various monitoring, measuring, and communication infrastructure generally has an opportunity. It will allow you to build an efficient and resilient grid, but it also brings the various threats of instability and security concerns. From a cyber attack or voltage instability or power quality disturbance. Specific to power quality disturbance events, how would you address the power quality in a machine learning backdrop? How would the power quality disturbance events get addressed? The power quality disturbance events, you collect the data. The data generation is available, meaning events are there, so events are generating the data. Then there is a feature extraction and selection, which is about classification. Then the optimization will happen, and then classification of these events. So based on those events, based on the classification of these events, we identify what would be the cause, and then there will be prescriptive suggestions which are going to the system operators to handle the power quality disturbance. Let's take another use case like optimal load shedding. Optimal load shedding, optimal power flow, the cost outcome stems from growing need of the algorithmic based long-term and medium-term planning methodologies in the power networks. Basically, the methods are based on supervised learning for predicting the cost and a feasible solution of optimal power flow. This takes the active and reactive values as input vectors, along with the voltage magnitudes and angles on the buses, and then it creates a data set. And this is used in many studies, and coming up with some patterns of optimal power flow, the results have been very effective here. Then the third and the most interesting for me, because basically I'm more a power system protection person, is the power systems use case. Here, there are a number of use cases. Of course, the requirement of power systems will never change. Power system protection will never change. It will remain to be speed, sensitivity, and selectivity. There is no way this is changing. Come what may, even if the technology goes something with quantum computing, something else happens, the protections activity will still remain requirement to be very sensitive, selective, and have the right speed to isolate the faulty, detect and isolate the fault as soon as possible, so that there is minimum damage of equipment and people, or rather in the other reverse order, minimum damage of people and equipment. Okay. With the penetration of renewable energy, what is happening is the power system situations, and the way we understood when there is a short circuit fault, when there is a three-phase to ground fault, how does the other phase behave? What is the kind of negative sequence currents that are coming? These are all some things which we have studied for so long, but with the introduction of renewable energy resources here, the tasks of classification, location, phase selection, isolation, all these become increasingly complex, because the conventional methods have some problem or the other, because we always consider certain threshold conditions. We identify one particular phenomenon of either current or voltage or the sequence currents, and then say this is the characteristics of this fault, and we create thresholds for we find a way to identify, measure that quantity, and then create a threshold and have a protection, meaning identifying the threshold and tripping the breaker has been our normal way of looking at things. But then with the introduction of these renewable energy resources, there are a lot of changes that happen. Here, supervised learning with an input vector comprising of the raw values of power signals, sequence components, wavelet decomposition, etc., have found to be effective. Let us go in a little bit deeper and see, meaning not deeper because we don't have so much time to go deeper. Let us look at a few more cases in as a specific in power systems. Say, let us take the case of power swing. Distance protection has been, this is a very widely used protection scheme, because there's a lot of voltage transmission lines, high voltage transmission lines, and this protection scheme is used extensively. But this has the protection principle possesses peculiar advantages, but also has some serious shortcomings. When you're talking about distance protection, we are always looking at the locus of the impedance. Okay, now we are considering the locus of the impedance, but power swing becomes a power swing which is not actually a fault condition, will also have an impedance locus which will not allow the distance protection to operate correctly. So we are always looking at how to block the distance relay during a power swing, and sometimes the fault resistances are so low that or rather the fault resistances are so high that you are seeing it outside the active region of the distance protection. So when you look at all these things, there are alternatives with machine learning where they use artificial neural networks based on the amplitudes of the three-phase currents and voltages and three measured phase impedances and their changing rates. They take them as inputs, and based on, since it's a supervised learning, you are looking at all the fault conditions and allowing the neural network to finally classify a condition which resembles any of the fault condition. Of course, all of these things require lots of data. That is the reason, instead of starting with artificial intelligence, we started with the kind of data that could be available in the modern world, modern power system world. Yeah. Then the next is the phase selection. The phase selection, invariably, we have always understood that the phase selection, especially when we are having auto reclosure, a single phase fault, and we want the system back in operation soon, we will require a phase segregated tripping. Meaning if it's a single phase fault, we want only that particular breaker to trip, and then also get back to find out if it's a transition fault to get it back onto the system again. So this is something which we have already always looked at as a big advantage. So if you want this, there is a phase selection aspect which needs to be introduced into the distance protection. Invariably, phase selection reduces or adds to the time of operation of the relay. So now, but apart from that, it's also the fact that the amplitude and the sequence component of the current have many shortcomings when it comes to distributed energy resources. Once you are having distributed energy resources, the kind of for some fault, when you are looking at a negative sequence current, and then you make a phase selector based on the presence of the negative sequence current above a certain value, and the presence of distributed energy resources, especially like solar or wind, there is the inverter which is coming into picture. When the inverter comes into the picture, the negative, there is in general there is a suppression of the fault current, and the negative sequence current will not reach the threshold at all. So you always have a problem with the phase selection then. But then there are some ML models which are based on supervised learning, successfully implemented fault classifiers, which can be effectively used both for conventional and non-conventional energy sources. See, invariably, when you're using the current component, which is the most used component for identifying the phase selection, meaning for doing the phase selection, there is always there is a shortcoming whenever distributed energy resource, non-conventional energy resource is introduced into the system. So this invariably can change when you are changing the when you're looking at machine learning based a solution for phase selection. So fault location is very similar. The accuracy of the fault location is severely affected by the presence of varying fault resistance. There is a good amount of literature which is wherein ANN based models are used for fault location. This uses the rate of rise of the incremental current, which has been which seems to be giving an accurate location of the fault. And a transformer differential. So this is also something which perhaps we can look at in a little bit more detail in the next slides, in the next few slides. Basically, you could use many methods. Use of artificial neural networks or random forest to effectively identify the inrush. So basically, in a transformer, what is the main thing that we are constantly looking at? We want to look at we want to differentiate a internal fault from an inrush situation or overexcitation situation. So under both the conditions, we would not want the relay to trip, but only during an internal short circuit fault, we would expect the relay to trip. So this is something which is which can be also solved by using the machine learning. This aspect of differential protection can be used solving the machine learning techniques. And also this unit commitment control of smart grids. See, reinforcement learning model, which is used to determine which generator can be dispatched so as to minimize the cost, has been used in many literatures. This reduces the complexity caused by the linear programming or mixed integer programming. Before looking at machine learning modules, this unit commitment control was more coming from the more solved by the linear programming methods and mixed integer programming methods. But the complexity is largely reduced when you're using machine learning based or particularly reinforcement learning based models for unit commitment control. Then you have the asset performance management as well. There are a few other things like electricity theft detection. Data mining methods could be used. Profiles can be compared. It can be both. It could be used both. What you call supervised or unsupervised situation. The electricity theft is a major concern both in developed and developing countries. Although there is a low electricity theft rate in few countries like the US, there is an estimated loss of revenue of close to 4 billion per year in US alone. And obviously in places like India, we would see much higher losses or much higher theft losses. Detecting the potential electricity thieves is thus of interest to mitigate the losses. There are check meters and usage analysis which are identified as the patterns for patterns, and based on those patterns, change in the situation can always be detected. And they generally use the classification, clustering, and detection. Classification can be used with the labeled data. And if the labeled data is not available, non-labeled data can be used, can be also taken, and that predominantly becomes unsupervised learning. When I'm saying labeled data is the data which you are using for training, meaning you know the results. You have a certain data, you know the pattern because you know the results, and you are feeding that to the model so that it is able to recognize that pattern. So that is the labeled data. And the non-labeled data is a data where you do not have a fixed result. So you are going to give the data and the result, and the model will by itself identify the pattern. I hope unit commitment control, what it means is known to people, because we have a significant penetration of renewable energy in these modern grids. These sources of energy are unpredictable in nature because there is a lot dependent on the environment around you as well. So we are talking about but then you have a demand which is there. There is a forecast of the demand. So you will have to collaborate resources in order to achieve the demand. So you need to have a method to see to it that there is no loss of service at any point in time. So the kind of, there are reinforcement models which are available so that they minimize the cost of doing this collaboration of resources. It also reduces the complexity. It also reduces the complexity by doing it in the machine learning model way, the reinforcement model way. And when we are talking about transformer differential protection, perhaps maybe I'll slightly touch here. Pattern recognition and dimensionality reduction, because you're having so much of data. So pattern recognition and dimensionality reduction are major methods that will be used in the differential protection of the transformers. Both linear, there are two methods of analysis for data analysis. One is the principal component analysis, and the nonlinear neural network based curvilinear component analysis are considered. Both PCA and CCA use differential currents from the current transformers at the transformer terminals. So both of them are dependent on the face-to-face differential current that would be there. So all of them, they look at the current patterns only, but they are looking at patterns and they are looking at the dimensionality reduction because of the quantum of data that you are talking about. Okay, then we go to. We perhaps will not spend too much time here because there's I'm just looking at what to address here. What is the kind of data you're talking about in a differential protection? We are talking about voltage and current signals. They are sampled at 128 samples per 50 Hertz cycle in a three-phase system. That is, we are talking about 19,200 samples per second. And then this is a three-phase system. So every second you are collecting this data, and this data is subjected to the analysis, the analytics. It is subjected to analytics to identify the inrush versus the short circuit current. So this is the quantum of data that we are talking about. So now if you have to really, so although the analysis of large volumes of data often carries the promise to gain new insights, so that is what it tells, because we are talking about there's so much of data, and when we are doing the analytics, we will gain so much of insight, is what we have been harping on, and we have found algorithms to support us to do this. But we also have to keep bearing in mind that this raises issues in terms of computing complexity, time and memory consumption, workload distribution, and efficient processing of the results, because all of these are now CPU based systems. So when these things have to happen at some, when we are talking about protection, because they are all very close to the process, so there will be a CPU based system. So there is a lot of computing complexity which is involved. Now let us concentrate on one of the use cases, that is transformer use cases of 1 minute, of transformer differential protection. Let us consider the power transformer and its traditional protection requirement. The main protection used in power transformer is the differential protection, which is based on, it is based on the Kirchhoff's law of electric circuits. This protection scheme has excellent performance to detect the internal faults, but it can operate incorrectly due to magnetic saturation in current transformers caused by the DC component present in the fault current. Also, the other one that we are having very familiar with, and which is the most used differential principle, it is the percentage differential principle, which improves the performance of the differential protection, because it makes a comparison between the operation current and the restraining current, which are called as vector addition and subtraction. This allows reducing the negative effect of saturation in the current transformers. But then there are some methods to avoid the incorrect operation further due to the inrush currents during transients affecting the magnetic flux of the power transformer. The first solution was to include an intentional time delay in the differential relay to halt the relay operation for a certain time interval, typically of the order of 16 milliseconds. But this is disadvantage. This is a major disadvantage, because you are delaying the tripping of a short circuit current in case there is an inrush condition. Or rather, in order to eliminate the inrush condition, you are delaying the tripping of a true fault condition. Another method widely used is the harmonic current restraint or blocking. That is what we are, most of the modern power transformer differential protection has the harmonic restraint or blocking. So the presence of second harmonic and fifth harmonic block the differential element of the protection. So the differential relay self desensitizes during inrush currents, but the relay can detect short circuit currents. To do this, the relay distinguishes between the inrush current and the short circuit current by the difference in the current's wave shape. So basically, you are either looking at the waveform recognition or the value recognition. The methods are based on that is, to do this, the relay distinguishes between the inrush current and the short circuit current, as I said, by the difference in the current's wave shape. The methods based on harmonic currents do not work reliably in cases where the differential currents show low harmonic content. Suppose we are using a new magnetic, the core of the transformer is a new magnetic steel transformer, steel core transformer. The harmonic content will be so low that you will not be able to distinguish between the inrush current when there is a fault. You can't distinguish between the inrush current and the fault current. The transformer overexcitation is another possible cause of incorrect operation in a differential relay. There is an additional fifth harmonic restraint which will be included in the relay, and the waveform recognition algorithms are used to distinguish the faults from inrush to improve the relay performance. Now let us look at the newer alternatives. Till now we were discussing the traditional alternatives. In the newer alternatives of the power transformer differential protection, there are these dimensionality reduction methods based on principal component analysis, as I mentioned earlier, the PCA, and the curvilinear component analysis, CCA. The PCA constitutes a classical linear technique which is widely used due to its simplicity and efficiency. The CCA offers a multi-dimensional scaling which is based on the aim of preserving the maximum amount of data. Preserving the maximum amount of data and the data distances that are, when we are really looking at the algorithm, we realize that there is a data distance which you will be considering, and they preserve the maximum distance, maximum amount of data. However, both these techniques have a kind of drawback because they have the capability to their capability to capture the non-linearities can rather be limited. Of course, there are variations to the CCA now, like CDA, curvilinear distance analysis, to address this. However, let us now look at the CCA and PCA. But when we are using these algorithms, the goal of the algorithm is first to reduce the dimensionality of the high dimensional data space formed by the differential currents to find the projections resembling the characteristics of the original space. Basically, see, we are talking about what kind of we are talking about the differential currents, I differential between A and B phases, I differential between B and C phases, I differential between C and A phases. So we are having, in a three-phase system, three currents, and at the kind of sampling rate that we are talking about a huge amount of data. So basically what the PCA does is, it reduces the dimensionality. Say for example, they use the model analysis, neural networks are used for the pre-processing both in PCA and CCA case. A pattern recognition is carried on using the different features of the differential current. In PCA, the three-dimensional differential signal is sampled at 8 kilohertz, which gives you 128 samples per cycle, and a sliding window of half a cycle is used. The sliding average window, which you are seeing here in the right-hand side of the slide, it uses half a cycle, which is 64 samples per cycle, which is 64 samples per cycle. Now, when on the other hand, CCA uses a whole cycle window sampled at 4 kilohertz. 4 kilohertz frequency, which again brings it back to 64 samples per cycle. This process is depicted in this in the figure. The PCA and the CCA algorithms consider the current transformer saturation phenomena and deviations in the power system parameters. Both algorithms were proven by means of time domain simulation of distinct scenarios as variations in the transformer load, source impedance, turn ratio, BH curve of the current transformers, and in all of these cases, it could distinguish between the internal short circuit current, inrush, and overexcitation conditions in all the cases. So this is one literature which indicates that this is pretty successful machine learning method to handle the transformer differential. If we have to go a little bit deeper into the PCA, PCA is a powerful multivariate statistical technique employed to transform a set of variables along orthogonal axes or reduce the dimension, that is the number of variables. The PCA was further, the PCA aims to reduce a database with many variables to a lower dimensional space while losing as little information as possible. Okay, the main utility of PCA is that it allows the study of the multidimensional phenomena where some or many of the included variables are correlated with each other in varying degrees. So, so whatever data is available, there is a correlation. They go ahead with, they identify the correlation and the variance, both of them. So because of that, it is very successful in identifying the difference between the short circuit current and the inrush current. It applies a transformation which results in an orthogonal rotation of the original data. The new orthogonal vectors, they are determined and they contain most information of the data variance. They find the linear combination of these variables and certain multidimensional property is considered, and then they exhibit the maximum variance. So it has got maximum variance, at the same time they are intercorrelated with each other, and hence you are able to identify the pattern for different kinds of currents. The main benefit of PCA is that even after you remove the reduction of the dimensionality, reduces the number of variables, but it importantly keeps the dynamics of the original data intact because of the both the correlation and the variance factors that are considered. So the PCA extracts the characteristic features from the transformer differential current waveform during distinct scenarios. During the various scenarios, these features allow to classify the current signal as inrush, transient, or short circuit inside the power transformer. So PCA is one method, and the CCA is the other method, that is the curvilinear component analysis, where the CCA is implemented as a self-organizing one-layer neural network. That is what you see here on the rightmost part of the slide, where you see it is a one-layer one, wherein you see the DSP is the digital signal processing stage, then IL is the input layer, that is the single layer which we are talking about, and the output layer, and the binary decision signal, that is the +1 and -1 that you are seeing there. The IL input data consists of column vectors which have got a dimension of 1 to n. It has got the vectors which are n in number. That is, there are n vectors with each one has a dimension of 1 into 192. 192 is coming from the samples that we are talking about. Those vectors are in turn formed by 3 vectors basically. It is 64 into 3 because we were talking about 64 samples per cycle. The 64 samples per differential. That is, you have the delta, that is I differential, delta I A minus B, delta I BC, not A minus B, it is delta I AB, that is the differential current between phase A and phase B, differential current between phase B and phase C. Then you have the differential current between phase C and phase A. So each one is 1 into 64 dimension. So all 3 put together, it is 192. These 192 elements are stored for every single vector and arranged as a training matrix. The training matrix will have a dimension of 192 into n, where n is the number of test cases that you could identify. The test cases can be running in hundreds because we are talking about R phase current, R phase short circuit, inrush current, various phenomenon multiplied into the 3 phases. We can talk a huge number of test cases that can be planned. So from this, it identifies the decision signal. It identifies the decision signal, and then that makes it capable of identifying between the inrush and the short circuit current. So that's how the CCA works. if you look at one more overcurrent relay coordination in distribution systems, when you're having the distributed energy resources in the system, you will find that relay coordination is a big what do you call it's very complex, and it could be a very big challenge. What you see there depicts the scope of the deep reinforcement learning which is used for relay coordination. I'm just going at a very high level as to what is identified, meaning the ML life cycle is seen, and what you do in each of these stages is seen. Basically, what happens is, because of the presence of in-feed, the short circuit level can change dramatically, because of which the coordination of the overcurrent relay may fail. Because as we mentioned, the distributed generation can go on and off in a system. And because of that, the short circuit levels and the fault current paths can be different. And hence, it is really required to have an adaptive relay coordination strategy. So we were working on this this phenomenon with I have one person in my team with whom we have been trying to do this, trying to use the reinforcement learning to come up with some kind of a coordination strategy. Whenever the system changes, how do you go ahead changing the time setting multiplier and the PMS, the plug multiplier, how do you change it so that you are able to maintain the coordination intact? So here what we are doing is, we will consider each of the relay as an independent agent. And when you consider one relay, all the other part of the network, including the other relays, will become the environment for that specific agent. The state of the agent is its own, the present TDS and the PMS setting, and the current time of operation of its backup or tertiary relay. So that will become the status. Now, the penalty and reward at each time step is given based on the maintainability of the coordination time interval between the primary, backup, and tertiary relays, along with the constraint that the overall time of operation should be minimum. So this is how you are turning the coordination problem into a reinforcement learning environment problem. Each relay continues to tinker with its time dial and plug multiplier setting during the training process, and determines the optimum action which will be needed to see to it that it is getting the maximum reward. And as the dimension of the state action matrix increases exponentially with the increase in the number of relays, DRL, meaning deep reinforcement learning, is used, and particularly to find an appropriate Q value at each state. And neural network is used to approximate this Q value at each time step, which can be precisely calculated if the state action matrix is maintained, and generally used if the dimension is small. So that is how we do this. And one other use case, which perhaps I will complete it in the next 5 minutes. I have already short my time by 10 minutes. Just let me not go in too deep, because this is again talking about the situation in utility industry. There's no doubt about the challenges that we face today: aging infrastructure, reliability. Then you have the asset information everywhere, distributed energy, spending justification, aging workforce, cyber security, etc. So we need to be in a full control of the asset management risk, and risk is managed cost efficiently. It has to be managed. And you also need to look at lower maintenance, overall maintenance cost, lower replacements costs, etc. It needs to be the whole strategy for asset performance management should be changing based on the strategy. You should be able to be agile to adjust to the changing business environment. Okay, so from that perspective, for transformers again, the APM, there are solutions wherein we use ML based. It could be anything, but this is just a framework which tells you any model can be used. All the first is data collection, then you have the analyze and predict. It could be expert models. When you're talking about expert models, these are really the physics based models, meaning first principle based models, or it could be used, we could use statistical models, or you could use machine learning model. So, and based on that, there is you also analyze the risk of your assets, meaning all assets are not having the same priority and the same risk impact. Or meaning same impact on the system, meaning some transformer which is in the last leg may not have the equal priority of a transformer which is really in the center of the hub of that grid and having many multiple connectivities. So you base all your performance management or your even the maintenance activity based on this kind of data. That is, as a enterprise, I will know what kind of assets I'm having, what is the priority of these assets, and then having machine learning models, I will be able to come up with a strategy, performance management strategy, wherein even my maintenance or changing of transformers, changing of age transformers, I do it based on the analysis that is coming out and the prediction that is coming out. So this is one other example, one other use case which you would see for using machine learning in power system operation and control. I have a number of references which I have made, and that completes my session.
Thank you, ma'am. Ma'am, there are some few queries out there. Can you read it out?
Yeah. Perhaps would we, yeah, I'll try to answer them. If I'm not, meaning I have a hard stop of 4 o'clock because I have a meeting at 4 o'clock.
Okay, ma'am. So only two
What I
questions.
could do is I could take the questions and then maybe I can answer them via mail to you, Mr. Deepak.
Okay, ma'am. So I will take the questions and I will mail to you, ma'am, after the session.
Yeah.
Okay.
So I could answer them.
Okay, ma'am. I will take the question and I will mail you by today evening.
Right.
Okay. Thank you, ma'am.
Can I stop sharing now?
Yes, ma'am.
I don't know how to.
No, ma'am.
You have to take it out, right?
Change the.
Yeah.
Question.
No, it's here. It was there. Stop sharing. Yeah. Anyway, thanks a lot.
Okay.
Thanks a lot for giving me this opportunity, Mr. Deepak. The only problem with the virtual this one is that there are a lot of questions, and you have to read the questions. And when I'm talking, I'm not able to read the questions.
Okay, ma'am.
Okay, maybe there are some of the questions which I'm seeing. What is the restore operation practice in case of microgrids as it results in unnecessary trips of DGs during temporary faults? This okay, this is a little bit lengthy answer. I will write it for it. And then how data collection is possible for real-time application. Are these waveforms measured and stored online? Real time, first thing is that all of the equipment which we are talking today, like relays or even disturbance recorders or PLCs or DCS, wherever, whether it is in power systems or in the industrial environment, they all have the signal processing. So when the signal processing is done, all the real-time data is already available. So that is what I was talking about in the differential protection as well. We are always continuously looking at I differential between two phases, and every instant that I differential value is sent to the place where these machine learning algorithms are running. So based on that, they are making the decisions. So when you are looking at any of these things, there are two types of data: the real-time data, which is going immediately into the when it is coming to protection, and when it comes to protection and control, real-time data is immediately sent to the consuming object, whether it is relay or to SCADA or wherever it is coming immediately. But then when we are looking at some other kind of analysis, which are really not real-time analysis, that is when we are looking at storage of the information. I hope I answered the question. The other one, I will answer it later.
Okay, ma'am. I'll share you the questions later.
Okay. Okay.
Ma'am.
Thanks a lot.
Okay, thank you, ma'am. Thank you, ma'am.
Thanks a lot.
Just
thank you very much. Yeah.
On behalf of Power and Energy Group NIT Calicut, I would like to express my sincere gratitude to Padmasri Krishnamurthy for having a great session on AI ML application in power system operation and control. The session has given a clear picture about artificial intelligence, machine learning and its types, deep neural network, life cycle of ML model, and an overview about the application of AI ML in power system applications like power quality disturbance, optimal load shedding, protection system, etc. Thank you so much, ma'am, for spending your valuable time and effort with us. I hope this session would help us in forming our curriculum and research work. Thank you, ma'am.
Thank you, ma'am. I'll contact you soon, ma'am, after the session. Hello, ma'am.
Thank you very much.
Okay, ma'am. I'll mail you the questions and everything after the session.
Yeah.
Okay, thank you.
Thanks a lot.
So much.
Yeah.
Okay.
Bye.
Participants, you can send me the queries or like through my mail after the session. Okay, because right now once we close this chat box, it will be so the next session is about to start. Okay, so if you have any queries, please mail to me. So I'll mail those questions to ma'am by today evening. So hopefully we'll get by, or even after this FTP also we'll get in touch with ma'am as well. So I can answer your queries. Okay, thank you. So please mail me these questions so that it will be helpful, because now I can see many questions are coming. So there is no option to I have to type it and save it somewhere. Okay, so please message all those questions or your queries. So I'll mail to ma'am itself. Okay, thank you. Polling will be there, and now our next session will start by 4. So you can continue. Thank you, Mira. Hello, ma'am.
Yes, Deepak.
Okay, ma'am. Anything to say, ma'am?
Next session, when it will be starting?
4 o'clock.
4 o'clock.
So you can have a poll now. Subin? Soon it will be there. Just a minute, we are creating the poll soon. Polling about to start, just a minute.